Hello everyone, my name is Cole Brittain, and I am currently conducting research on the effects of substrate on fish passage at Colorado State University. I'm very grateful to have this opportunity to discuss fish passage with you all, since this field has been rapidly growing in importance and prevalence over the last couple of decades. Trout Unlimited's wonderful mission statement is to conserve, protect, and restore North America's cold water fisheries and their watersheds. I believe restoring connectivity along a watershed is the most immediate and greatest way to positively impact a fishery. Here is an image from 2015 of the cold water transition zones for trout here in northeastern Colorado. The red and yellow dots indicate existing and potential barriers trout will encounter while fulfilling various life history stages. Many more barriers exist lower down, which are not illustrated here because those barriers affect more warm water species. You can see from this image that in-stream barriers are excessively fragmenting habitat, preventing trout from important food, refuge, spawning, and recruiting opportunities. In-stream barriers that create a potential for fish passage come in many forms. For instance, an undersized culvert here on the top right can easily become a height barrier during the majority of the year, preventing any fish that cannot jump this distance from moving upstream. On the bottom left is a large diversion on a smaller order creek in Wyoming, yet it blocks upstream movement while actively diverting water, which usually takes place over the spring and summer when fish are most active. On the bottom right is a larger barrier for water diversion that exists on the South Platte River right before Brittain. Water will be diverted almost the entire year except over winter months, when fish are moving much less frequently and are not migrating. In the top left, this last image is of a large hydroelectric dam on Blue Mesa. Fish passage both upstream and downstream does not exist for this large river containing large migratory species. In-stream barriers come in many forms, and it only takes one to fragment a river and imperil species present. The goal of fish passage is to overcome fragmentation and provide connectivity for riverine species, which use the waterways to fulfill necessary life history traits. Many innovative ideas have provided connectivity, but only a few provide effective solutions, much of which is determined by species and the type of barrier. For instance, the top three pictures show fishways that have been installed throughout the world but are only effective for strong performing species. The picture on the left is a baffle-style fishway, which creates pools for resting and small sprinting distances for fish to navigate upstream. The middle picture is of a fish lift, which acts like an elevator taking fish from the bottom to the top. The last picture is of a classic pool weir for fish species where you can see a large salmonoid jumping from one pool to the next. These fish passage structures have many problems, mainly the fact that they only allow passage for large, fast-swimming, and high-jumping species. Another problem is that they lack attracting flows for fish to identify the structures as suitable. The bottom of the slide shows the new and very cool salmon cannon, which you feed the fish into a tube and it will transport it up and over the steepest of dams. Although this overcomes the steepest of gradients, it is not practical for most areas of the world and all species, since every single fish needs to be captured, then fed into the machine by hand. For all of these structures, it takes a lot of money to move a small proportion of fish that are migrating. Although these are solutions, they are not extremely effective at providing connectivity and restoring a diverse and healthy river. Here are some images of rock ramp fish passageways. These are by far the most prevalent fish passage structures in Colorado and will continue to be. They are relatively cheap to install, they take very little maintenance, they operate all day, all year, and can pass all species if, and I stress if, correctly built. Their largest drawback is overcoming large height discrepancies, which I would then suggest either a fish lock or a natural side channel to overcome. For the vast majority of in-stream barriers in Colorado, the rock ramp will be ideally suited. The bottom three pictures is a progression of a culvert I helped replace in the San Luis Valley for Rio Grande natives. Now, I believe your TU chapter will be undertaking a similar project, helping to replace a culvert barrier on Pine Creek. Now, I would like to bring your attention to the top middle picture, where a structure recently built on the Poudre River in Fort Collins was mimicked from the model built at Colorado State University to determine ideal passage conditions for all species. Now, it is a trapezoidal shape and contains roughness elements in the middle to break up flow and create ideal hydrologic conditions for fish. Here is a diagram of the fish passage structure in the lab that I am currently working on. This flume was built by Tyler Swart while he was getting his master's. Tyler is a CPW biologist that recently gave an update to your chapter in February on the state of the South Platte. I have since retrofitted the flume for my own purposes. The flume utilizes a recirc system in order to not waste water. The water is stored in the sump, where it is then pumped up to a head tank on the top right. It then spills into the flume at a steady rate and runs down the flume over 4 antennas listed as A1 through A4. The water is then collected and heated or cooled as necessary before returning to the sump. Both flow and temperature are the main cues fish use to migrate. By keeping the flume at a steady temperature of runoff conditions and maintaining a steady flow, fish have all the incentives they need to give their best effort at navigating the flume. I have also included a photo on the right of PIT tags. PIT stands for Passive Integrated Transponder Device. The smallest 2 PIT tags are 8 millimeters and 12 millimeters, about the size of a Tylenol capsule. All fish in this experiment have been tagged so their progress up the flume can be tracked by the antennas. After downloading the antenna information, we are able to determine to what extent each fish was able to navigate the flume. Here is a picture of the actual lab and fish flume. The holding tanks below the flume house 3 different species, which I used to test the variable in question. And here is a look inside the flume. My experiment is testing the effects of substrate on rock ramp fish passage structures, and in this picture you can see that I have mounted coarse sand to the floor of the flume. Tyler Swart, my predecessor, studied slope as a variable of fish passage, as in the slope of the flume. During his studies, he chose 3 species to test, and I have chosen to use those same species in my experiment. In order to develop fish passage for all fish, then your limiting species need to represent the poorest swimmers. It is also necessary to test a number of small-bodied species in order to account for differences in physiology and swimming behavior. Small-bodied native fish were chosen due to their reduced swimming capacity. By developing criteria for these species, we are, in fact, developing fish passage capable of accommodating all species present within the river. Fish for this study were chosen based on their swimming performances from Ashley Fick's research conducted at Colorado State University. The Arkansas darter is by far our smallest species, only averaging approximately 2 inches long. They are called darters because they only have fast twitch muscles and therefore swim in bursts. From our studies, we have realized that they use their pectoral fins to hold on to objects and may use this to help them navigate a fishway. Their small size and poor swimming ability makes this our limiting species. Their performance will also mimic first-year fish due to size, so we know if fishways are precluding certain age classes. The Stonecat is a very small-bodied native mad tom. Their average size is approximately 4 to 5 inches. They were chosen because they are a benthic species with poor relative swimming capabilities. They are very similar to, say, a sculpin. And the last species chosen is the Flathead Chub, averaging around 4 to 5 inches as well. As you can tell from the picture, chubs are streamlined with nice caudal tails, making them very strong swimmers for being so small. They most likely resemble juvenile trout and will outcompete the other 2 species. It is necessary to have this range of species in order to accommodate different swimming styles and sizes. It is also pertinent to keep testing all of these species under the assumption that just because something positively affects one does not mean it doesn't negatively affect another. Here are the results from Tyler Swart's study on slope. You can see here the results of the 3 species we discussed. The degree of slope ranges from 2% up to 10% and is located on the left of the image. The numbers on the bottom represent the distance from the bottom of the flume to each antenna. A1 through A4 represent the 4 antennas used. Within the bars are the percentages each species was able to make. For instance, an Arkansas darter at 10% slope successfully made it to the first antenna 72% of the time, and only the second antenna 1% of the time. None of the darters made it to the third and fourth antennas. From these graphs, you can see that the Flathead Chubs are by far the strongest performers. The Arkansas Darters are the limiting species, and the Stonecats lay between the two. Now, for my experiment, I needed to select a slope that I could test all these species against in order to determine if substrate was helping or hurting them. I chose to test all species at a 6% slope in order to determine how much it is helping the darters and stonecats, and also to ensure it is not prohibiting the flathead chubs from passage in any way. The variable I am currently testing is substrate, to determine the effects that substrate will have on fish passage. Since I am currently in the middle of testing my substrates, I only have the preliminary results from two, both coarse sand here on the left and pea gravel here on the right. I will also run a control experiment with no substrate and another experiment with small cobble, which will at least be twice as big as a pea gravel. This substrate will fill the interstitial spaces between the roughness elements. The roughness elements, which look like small rocks, were part of the original design of this rock ramp to reduce velocity and also provide velocity refuge for fish, without creating hydraulic barriers the way a baffle might. These rocks are molds cast from an actual river rock used by Tyler Swart during his experimentation. Here is a gradient chart representing hydraulic measurements I took at 18 different cross-sections within the flume. The flow moves from right to left, and the red indicates high-velocity areas. The bottom portion of the flume is slower due to backwatering, which was purposefully created in order to provide a pool so that fish could recover and attempt the flume again. I'd like to point out that the trapezoidal shape of the flume creates slow water margins on the sides of the flume. Now, each trial lasts for 22 hours, giving each individual multiple opportunities to navigate the flume. If fish passage is improved due to substrate, our next question will be whether or not it is because of hydrology or physiology. In other words, is passage success improved because the water is moving slower due to the substrate, or because fish are utilizing the substrate differently? I will take hydrology measurements at each substrate in order to compare the difference of encountered velocities under each condition. I have listed some preliminary results for you here, but I have a small disclaimer. It is important to note that these numbers have not been modeled. The antennas do not always detect 100% of the tags, therefore it is necessary to model detection discrepancies to arrive at the true detection numbers, which will be larger than the ones I am reporting. For comparison, I have included Tyler Swart's study of the same experiment with no substrate, which will mimic my control. However, his numbers have been run through a model in order to account for detection discrepancies where mine has not. Now, these first results are for the Stonecat. From the control experiment, Stonecats are showing high fatigue rates in the last quarter of the flume. However, as substrate sizes increase, we notice the passage rates also increase. Stonecats are responding to larger substrate with dramatically higher passage probabilities, and this is fantastic news. The next set of results are for the Flathead Chub, which is very straightforward, as you can tell. Chubs are the race horses of the group. They made it to the top consistently without much effort. It is important to note that substrate has not negatively affected their performance. The last set of results are for the Arkansas Darters. They are definitely our limiting species as they consistently underperform the other two species. Coarse sand showed significant improvement at antenna 2, but similar results from beyond. On the other hand, pea gravel had some truly amazing results. Darters that are previously unable to ascend a 6% slope now have a 24% chance of making it to the top and beyond. Not only does substrate help, the size of substrate is very important. Pea gravel might be just large enough to allow these Arkansas darters to utilize their pectoral fins, as we predicted. However, after looking at the results for pea gravel, there is one troubling element, and that is the detection rate at antenna 3 is the same as the detection rate for antenna 4. My antennas have very short detection distances, and I was curious why I was possibly missing fish. I initially thought that darters would use their pectoral fins to hunker down behind those roughness elements to get rest, which in turn would give them a high detection probability. So to determine why I was not detecting these fish, I pulled up a bucket and watched these fish run. I quickly found out why I was having so much trouble detecting these fish on the antennas. Here is a very cool video that shows the darters utilizing the side margins with low velocities. But even more than that, they are beaching themselves on the side to rest, recoup, and move forward. This explains why I am missing them on the third antennas. They are going out of my antenna's range, out of the water, in order to make it to the top. This also indicates that fish are improving passage probabilities due to both hydrological and physiological advantages the substrate created. Now I will continue this experiment, testing both a control and a larger substrate. After I've completed this, I will run a brief experiment over the effects of light on fish passage before I attempt to publish.
Why aren't these bugs deeper? Why don't they move aside so I can stretch underneath them? Now he's up there.
All you have to do is flick that tail once and he's off that screw. But he's still right there. Now he's back down here. Going forward, I hope that these results will help inform water managers of how to build a more effective fish passage structure by utilizing an ideal size substrate. I hope you enjoyed this quick foray into fish passage. If you have any questions, please feel free to reach out to me. Thank you for your time.